Section 10.3, double angle and half angle formulas. We are actually going to look at the double angles, and half angles you can kind of look at on your own, but we're not going to emphasize the half angle formulas here in this section. We'll develop those in calculus. So we're adding to our long list. We've got sum and difference formulas for sines and cosines and tangents. And now we're going to develop some of these double angle formulas. And they are derived from the sum formulas or difference formulas of our sine, cosines, and tangents. So here we see the derivation for a double angle sine formula. And we start out with sine of alpha plus a beta, our normal sum formula for sine. And we know that that gets into the situation of a setup where I have sine, cosine, cosine, sine. If, though, we have, instead of an alpha or a beta angle, we have another alpha angle, we get a situation where this alpha plus alpha becomes 2 alpha, and this is where we get double angle from, twice the same angle. And then we replace all those betas with alphas. We end up with a sine alpha, cosine alpha, plus another sine alpha, cosine alpha. So we have 2 sine alpha, cosine alpha. So there's our double angle formula for sine. If we carry the same concept with cosines, again, changing the beta angle into another alpha angle, replacing all the betas with alphas, we get that the cosine of 2 alpha is equal to, one of the formulas is cosine squared alpha minus sine squared. Now we can develop this one further. Like, how did we get to this point? Well, we go back and we take a look at our trig identity, Pythagorean identity, and we know that cosine squared plus sine squared is equal to 1. So if I just simply solve this for cosine squared, Alright, so we solve for cosine squared and we get 1 minus sine squared. And if we replace this cosine squared with a 1 minus sine squared, we get a 1 minus sine squared alpha minus another sine squared alpha, which is where this 1 minus 2 sine squared alpha is coming from. And if we did the same thing with the Pythagorean identity, but this time solved for sine squared alpha, we get 1 minus cosine squared alpha. And again, this time replacing the sine squared alpha with a 1 minus a cosine squared alpha. That's how we get this. We have that would be a negative that has to distribute. So it would be a negative 1 plus a cosine squared alpha. And there's where the 2 cosine squared alphas minus 1 comes from there for that. So double angle for cosine, we have a couple different options we could work with. And then our double angle tangent. Again, replacing the angle beta with the duplicate angle alpha. Now we get 2 alphas. Tan alpha plus tan alpha becomes 2 tan alphas on the numerator, and 1 minus tan alpha becomes 1 minus tan squared alpha in the denominator. And now we have all of our double angle formulas for sines and cosines and tangents. So we'll be coming back to this page and referring to it as we go and work through these problems. So our first one here, we're going to simplify sine squared alpha over 2 minus cosine squared alpha over 2. And remembering that what comes after our sine or cosine or tangent or any of our reciprocal functions, this part of the problem is an angle. And maybe to simplify the way that this looks, we're going to do a little substitution here. We're going to let this theta value become alpha over 2. So now I get sine squared of theta minus cosine squared of theta. And this actually is the opposite of what we want. for our cosine, excuse me, we want cosine squareds minus sine squareds. So we are just going to factor a -1 out of this. We'll get a negative sine squared theta, and then plus cosine squared theta, which means we can now write it as cosine squared theta minus sine squared theta. And we know that that part of the problem, cosine squared minus sine squared, is equivalent to a cosine of a double angle. So we can just rewrite it as cosine of 2 theta. And then, I don't know where this double negative came in here. And then we have resubstitute. We get cosine of 2 and resubstitute in for theta this alpha over 2. And we get to see here that those 2's cancel. And we end up with our final simplified form of negative cosine of alpha is what that would all simplify down to. Let's try B. So we see we have some tangents involved here. And this, going back into our property or our double angles, we see that a tangent, right now it's set up in this format, that problem that we just had, where the alpha is the 157.5 degree angle, and that is going to then take us back to this setup, this form. So we're going to end up with a tan 2 alpha here. So there's our alpha. This becomes tan of 2 times this alpha angle. And that becomes the tangent of 315 degrees. And then going back, remembering 315 degrees, quadrant 4, reference angle of 45 degrees. We have a -1 and a 1 there, my tangent. And so therefore the tangent of 315 is equal to -1. So that's how that one simplifies. All right, now we have to recognize what double angles these come from. The sine is the one that is has just one formula, the one that involves the sine and the cosine. And the cosine double angle is the one that can have 3 different options: cosine squareds minus sine squareds, or 1 minus sine, 2 sine squareds, or 2 cosine squareds minus 1. And that is the situation we have here. So that 3 alpha would be equivalent to this angle that we're talking about, our double angle. So you could do a substitution thing here if you wanted to. You could let theta equal 3 alpha, or you could just leave it alone. So if it makes a little more sense for you to see it this way, then go for it. Solve it for that theta, and then resubstitute in the 3 alpha at the very end. I'm going to go ahead and just solve it as it was written originally: 2 cosine squared 3 alpha minus 1. We know that that comes from our double angle formula for a cosine of 2 alpha, but in this case, our alpha, the angle that we're referring to, is this thing right here. So this then becomes cosine of 2 times 3 alpha. It's kind of like doing the substitution. I'm just not doing it with theta. And that is cosine 6 alpha. There we are. Let's go ahead and just do the substitution method. We know that this would become cosine of 2 theta. You re-substitute 3 alpha in, which is what we essentially did in the one below. Cosine of 2 times 3 alpha. And we ended up with cosine 6 alpha. So either do the substitution or just play with what you have there. Recognize that one as a double angle sine. So we can take a look at sine of 2 again. Think of this as an angle theta. So if we do some substitution, we can say that this is 2 sine theta cosine theta. And we know that that is the same thing as sine of 2 theta. So we can just resubstitute for theta this alpha over 2. Those 2's get to cancel, and we end up with just sine of alpha. All right. We've seen these type of problems in our sum and difference formulas for sine and cosine. And they are the same type of setup here, where I've been given some trig ratio and some angle in a certain quadrant. So here we have an angle alpha that is hanging out in quadrant 4 between 2 pi and 3 pi over 2. And we want to find the sine of 2 alpha. So we want to find the double angle of this situation here. So let's go find, first of all, our sine values. So we draw a little sketch. We're in quadrant 4. We have this angle that produces a ratio of cosine of x over r of 5/13. There's our angle alpha that we're referring to. So we have a situation where we get 13 squared, 169, minus 5 squared, 25, we get 144. And square root that, and that means this side of our triangle, because it's in the negative y area, has to be negative 12. All right, we now have the piece that we needed to be able to find the sine of this angle. So the sine of this angle alpha is equal to negative 12/13. So we are to find sine of 2 alpha, and that is the same thing as 2 sine alpha cosine alpha. And we now have cosine alpha and sine alpha. So we go ahead and come up with sine of 2 alpha is equal to 2 times sine alpha cosine alpha 2 times negative 12/13 times 5/13. And we get negative 120 over 169. And let's see, can we reduce any of those? No. So there's our value. sine of 2 alpha in that situation. Let's do some tangents to see what happens with this. So now we have a tangent of some angle u is equal to 1/2. And we are in a quadrant that puts us between pi and 3 pi over 2. So we're in quadrant 3 with this angle. And here's our angle u. And we have this ratio of 1 over 2 for our tangent. So we have -1, -2, 2 squared plus 1 squared, square root of 5. The hypotenuse on that triangle right there. And we're looking for the sine double angle. So we're going to go find cosine of u and sine of u. Cosine of u is our -2 over root 5. And if we rationalize it, we're going to get -2 root 5 over 5. Sine of u will equal -1 over root 5, or -root 5 over 5. And so our double angle says that sine of 2u would be equal to 2 sine u cosine u, which means 2 times -root 5 over 5 times -2 root 5 over 5. This becomes -4 times, positive 4 times 5. So we have 20, because the square root of 5 makes a 5. 2 and the -2 makes a -4, and that negative with the square root of 5 makes positive 20 over 25. Leaving me with 4/5. And more of the same, ending up with just putting ourselves in different quadrants. This time we're looking for a double angle for a cosine. We're now in a situation where you're in quadrant 4 once again. And our tangent value of our alpha spins us all the way around it there, gives us a -5 over 8. So 64 and 25 is 89. So this is the square root of 89. That's our hypotenuse. And for our cosine double angle, we actually, again, have the 3 options here. We can write this as cosine squared alpha minus sine squared alpha. We could do 1 minus 2 sine squared alpha, or we can do 2 cosine squared alpha minus 1. Those are our 3 equivalent expressions for a double angle cosine. We're going to need cosine alpha and sine alpha anyway. So let's see, a cosine alpha would be 8 over root 89, which becomes 8 root 89 over 89. And our sine alpha is a -5 over root 89, which becomes -5 root 89 over 89. All right, let's just go ahead and do our cosine squared alpha minus sine squared alpha option. So we're going to get cosine squared alpha minus sine squared alpha, giving us an 8 root 89 over 89 squared minus a -5 root 89 this, it's going to reduce. If I hadn't rationalized and just used 8 and the square root of 89 as the denominator, negative 5 and the square root of 89 as the denominator, this would have been 8 over the square root of 89 quantity squared minus negative 5 over the square root of 89 quantity squared. Well, 64 on the top minus a negative 5 squared, 25 on the top. And then the square root of 89 squared is just going to be an 89, so we're going to just get that as the denominator. And this ends up becoming 39 over 89. All right. And then we have cotangents. And again, a cotangent, we're trying to find a double angle for this cosine. We are once again in quadrant 3, between pi, 3 pi over 2. So angle U. Remember, the cotangent is an x over a y value. So I have a negative 3 over negative y. 9 plus 1 means that this hypotenuse is the square root of 10. And we'll go ahead and stick with double angle cosine. We'll just do the squared cosine minus squared sine value. But first, we've got to find these cosine and sine values. Cosine of u would be negative 3 over root 10. And we'll leave them, because we're going to square them anyway, we're going to leave them as unrationalized. And sine of u would be negative 1 over the root 10. So our double angle cosine says we're going to go back to our setup of cosine squared minus sine squared. And again, I could be setting up the other forms as well. So cosine squared, negative 3 over square root 10, square it. Negative 1 over the square root of 10, square that. Simplifies to a 9 over 10 minus a 1 over 10, 8 tenths, or 4 fifths. All right. Moving on. More simplifying, rewriting what I have here. So again, I'm recognizing that this setup here is a double angle sine. So I'm going to have sine of 2. It's going to look sine of 2 times this angle alpha. There's our angle alpha, 22.5 there. So simply becomes sine of 2 times 22.5, or the sine of 45 degrees. And then sine of 45 degrees, we know, is root 2 over 2. Here we have a double cosine. Where once again, there's my alpha. So I get cosine of 2 times 150 this time. Cosine of 300 degrees. And thinking about where 300 degrees, quadrant 4, where cosines are positive, has a reference angle of 60, and a 60-degree cosine value to 1/2. Another double cosine angle. Cosine squares minus sine squares is one of my other setups for double angle for cosine. And this time alpha is a pi. So this can be written as 2 pi cosine of 2 pi is equal to 1. All right, sine of alpha is 4/5. We are now in quadrant 1, and we're going to find the double angles of all three of these. Over here, quadrant 1, there's our alpha, there's our 4, there's our 5, we have a 3, 4, 5 triangle. And then therefore we can find cosine of alpha and tangent of alpha. And I think that's all we will need here. So sine of 2 alpha will be our 2 sine alpha cosine alpha. And this will become 2 times 4/5 and 3/5. So we get 24 over 25. Spread these out a little bit. Oh. How about cosine of 2 alpha? Well, we have, again, our three options. So let's go ahead with the cosine squared minus the sine squared. And in that case, probably going to run out of room here, so we'll have to move the tangent one down. We get 3/5 squared minus 4/5 squared, giving me 9/25 minus 16/25 or negative 7/25. And then lastly, our tangent. Our tangent simplifies into a 2 tan alpha over 1 minus tan squared alpha. So 2 times 4/3 over 1 minus 4/3 squared gives me 8/3 over 1 minus 16/9, and we'll have to make a common denominator there. So 9/9 minus 16/9 gives me 8/3 divided by negative 7/9. And then we will save it, change it, flip it. So 8/3 times the reciprocal of negative 7/9. 3 and 9 reduce, and I get 24 over negative 7. We could write it like this, negative 24 over 7. Alright, so just putting it into practice. More of the same. And then lastly, prove that sine squared x plus cosine, sine x plus cosine x squared is the same as 1 plus 2 sine x. Let's work on the left-hand side here. So we're going to FOIL this out. We're going to get a sine squared x plus a 2 sine x cosine x plus a cosine squared x. Just working the left side. And we end up with a Pythagorean identity. Cosine squared plus sine squared. We know that that's going to produce 1. So now I get 1 plus 2 sine x cosine x. And we know that 2 sine x cosine x is our double angle formula for our sine. So this simply becomes 1 plus sine 2x. And that equals what's on